Come and speak. Now I have this bio here, which is very impressive, but I've known Jack for a decade or more, so I was just going to ad-lib some really embarrassing facts about how awesome he is, how he's been passionate about computer science education since I met him, and he was a teenager at the time. I thought it was a bit weird. No, it was fantastic. He is the CTO of Connected Ed Code, and he's particularly keen on making tech accessible to students. I'm really excited about hearing about that in this talk. So, Jack, welcome. Come on up. Join us. Thank you very much.
Hello. Ooh, I'm on. Yes, very loud. All right. Sorry, too many layers. This is great footage for all of you online. Very sorry, I didn't plan. Alrighty. Alrighty, yes, cool, nice back on, sorry about that. Cool, so, yes, my talk today is about wrapping up the cruft, and what I mean by that is making wrappers to hide complexity. So, who am I and what do I do? Why am I the one to talk about this? Well, I'm a bunch of stuff. I teach at Presbyterian Ladies College in Sydney. I teach Cambridge Computer Science to grade 9. Since I wrote this slide, I'm also temporarily teaching at Emmanuel School in Sydney, teaching 9 to 12 while they sort out a new teacher because one's left. I'm the CTO at Connected Code. So our whole mission statement thing is connecting code with context, community, and curriculum. We do basically any kind of education-y thing. We make projects for people to do. We help with teacher PD. We come and run events. All sorts of stuff around tech education. And then I'm also a professional dungeon master. I run role-playing games for people. It's great team-building events. Come talk to me. Yay. Cool. So let's focus on the relevant one, which is Connected Code. We do all sorts of events. The big 4 events that we've done so far are, the first one was called Data Detectives, and with this we planned a whole murder mystery, just a fake murder, but a murder mystery, and we went to a school and had them develop all sorts of programs to solve the murder. Things like using moisture sensors to check whether a car had been in a car park when it had rained, and if they had been there when they said they weren't, well, that's a little dodgy, isn't it? Things like that. We ran Escape Artists, another incursion into schools where we went and we took a whole year level, all of grade 8. We assumed they had no programming experience beforehand, which was largely true. And in 3 days, they built whole escape rooms in about 8 groups. And these were moderately complicated, moderately large escape rooms with all sorts of things, RFID reading, ciphers to crack, lock boxes with solenoids and all sorts of things there. And we've worked with the University of Wollongong on a couple of CubeSat workshops. CubeSat being a little 10-centimeter cubed satellite, basically a little weather station. And we got the kids, again, variety of ages, variety of programming experience, some who've never done any, some who've done quite a bit. And we got them all to program this weather station, tied them to balloons, tied them to drones, flew them up in the air, and got atmospheric data out of that. So these have been typically aimed at high school students. We've done a little bit with primary school students. And one thing we do that I touched on a bit there is we aim for differentiation. We want to support all experience levels, particularly with school students. Even though coding is part of the curriculum, it's implemented at the moment pretty differently at a lot of different schools, and so we can't make any assumptions about what the kids are coming in knowing. So we want to give it so that the kids who've never done anything can learn and grow and have a fun experience and get excited about tech, but the kids who've done loads of programming aren't really bored because they're learning about if statements again for the nth time. So one tool we use for this are kookaberries. So, the Kookaberries are great. They are a little microcomputer made by the Oststem Foundation, which is up in sort of the Central Coast Sydney area. They run MicroPython, they're easy to use, they're flexible, they're fun. They're a lot like a BBC microbit, if you've used that, and they're a little less like, but still pretty similar to things like Arduinos and Raspberry Pis and so on. One great thing about these is that they've got a bunch of plugs on the back and they can have peripherals. You can plug in all sorts of things. So many things. And this is just some of the stuff that I've already written wrappers for. Now, how do we get it so that the kids can use all of these different devices and feel capable and like they're achieving things and get excited, even though some of these devices are quite complex and they're all wildly different? Well, we wrap up the craft. So, what do I mean by craft? I mean, really, the stuff that doesn't matter. I'm going to do an unconventional thing for a talk at a Python conference and start by talking about Java. So let's look at Hello World. There's quite a lot in Hello World in Java. And that can be pretty intimidating for a first-time programmer. And it's also very intimidating for a first-time programmer when you guide them through typing all this, and then they have a question, and they have a question about kind of most of it. What does static mean? And the typical response that I've seen is, don't worry about that for now. And the problem is, when you say don't worry about that for now, to a kid who's maybe a little unsure if tech's for them, what they hear is, tech isn't for you. This is bad. So, let's talk about the stuff here that doesn't matter. You know what, let's just go ahead and change the color of everything that doesn't really matter to red. That's a lot of stuff. So how about we get rid of all that stuff? That's better. Also, doesn't that look a bit like Python? So talk's done. If you just use Python, then you're good to go. Maybe not. Okay, so let's look at a bigger example, and we'll flash some lights. So we're going to make a little program that lights up the first 3 neopixels in this bar. It's going to light them up red, green, and blue in turn, and then they're going to stay on for a little moment, and then they're going to clear. And it's just going to do this forever. So here is all of the code for that. You don't have to read all this. I'll skim through it. But there's a few things here. We've got a whole bunch of imports. We've got some mysterious line here that initializes the neopixel bar, and it's weird because you've got to say pin, but then you tell it P1, and you've already told the kids that the P in P1 stands for pin, so you're saying pin 1, but I don't really understand that. Then you just got this 8. And then, in the loop, you're using indexes, and you haven't started on lists yet. This is an early program, so what is an index? And then after you've written in that you want that first pixel to be red, then you've also got to do write. And now I'm writing twice, but I don't really get why. So there's a lot going on here. So what we've done is we've put together a fancy little library that you can just replace all of those imports with, from connected code, import star. And then we've got a nice smaller program where we just say, hey, connect a bar light on P1. And they understand what a bar light is because it's the lights that are in a bar, and also you've told them. And that function does what it says. It connects a bar light. And then in your loop, we've got set pixel, and you set pixel 0. You do have to tell them about 0 indexing. And then you give it a color. And in fact, this function is actually really robust. If you want to pass in a string that's an hex code, that's totally fine. 3 or 6 characters, that's fine. With or without the hash, that's fine. If you want a string that looks like an array of the red, green, blue, that's fine. Handle all of those. Really misunderstanding proof, mistake proof. Because typing in 3 numbers or looking up a hex code is not the learning. Like, that's not the logic, that's not the computer science that we're trying to teach. That's a step. And then we don't have a right step. And then to clear it, oh yeah, I meant to mention that bit. And then look at the bottom here. To set it all back to black and clear it, you've got to fill it with zeros and then write, but we just turned it off and didn't write turn stuff on. But anyway, now we've just got bar.clear, and that clears the bar. And we like that. But that's a pretty small example. What about a bigger example? Well, one of the things that we wanted for our escape rooms was to have RFID readers. That way you could find various, I don't know, if your escape room was magical themed or whatever, you could find various potions and each could have a little RFID tag on the bottom, and then you could put that on the sensor and you had to get the right potions in the right order. Here's all the code to make the RFID reader work. Or actually, once we've all wrapped it up, here's all the code to make that RFID reader work. And now, yes, absolutely, that's abstracting a lot away. But you can't teach a grade 8 kid who's never programmed before how to implement an I2C protocol in 3 days. It's not going to happen. And so you do this, and then they can read a tag name and they can focus on the procedure and the logic and the steps and the problem solving, and they can do cool things that they want to do, and there you go. They understand it, they feel cool, they make a cool thing that gets them excited. So how do we wrap things up? Well, I focus on a couple of main points. The first thing I ask myself is, what do they want to do? And by this I mean, like, when I'm a student sitting down to work on a project, and I think, okay, next I have to do X, what am I putting in there? Well, the biggest and broadest one is make a device do something. I want to do something. And for a bit more detail there, we could be like checking a condition. They might not know the term condition, but they want to, see if some condition has been met, see if it's ready to do something, that kind of thing. They want to update the state. Again, might not know state, but state includes changing those lights, turning them on and off. They want to update state. And then, again, a bit broader, they want to get input or produce output. All of these are kind of verb statements. They're doing things. So that's their goal, and we want to help them get to that goal. So what bits make sense to them? This is the stuff that we're going to build off. So we build off good function names. A lot of the time in programming, we have function names that make sense if you already know what they are. I know that if I'm connecting to something via UART, that I'll use the UART function. But if I'm teaching a kid like, oh yeah, you're going to plug into this radio and then send the radio messages, yada yada, and so you type UART, what does UART have to do with radio? I don't know. It's just not related. And so a big emphasis is on good function names. And that's why it had names like connect bar light. It might be long, it might be a fair amount of typing, but it says what it does. And I think that's really underrated. The next is clear steps. This is what I was getting at with that NeoPixel initializing line there. It had a few steps that didn't really make sense. We were telling it connected on pin 1, but then we have to tell it that that's a pin, but surely it should know that, right? One of the things that I was always taught when I was learning to program, shout out to my mum, was don't ask the user for anything that you already know. I know if I'm setting up a NeoPixel or any other peripheral, I know if it needs a pin, right? And sure, I don't know what pin it's plugged in on. I've got to get them to tell me that pin. But I have to get them to tell me that the pin that they're telling me is a pin. That's known. So remove those unclear steps. Clarify things. Get rid of that 8. That 8, if you're wondering, is how many pixels are on the bar. But I, as the teacher in this scenario, I bought all those bars. I know how many pixels are on those bars. They don't have access to any other NeoPixel things. It's those bars. They all have 8. I don't need them to tell me it's got 8. They also understand, generally, if statements. And I did want to call this out because programs that just do the same thing every time aren't that exciting to the kids. They want to feel like stuff changes. And so, and it's generally pretty easy to explain if statements to them. The classic example is, if it's raining, take an umbrella. They're like, oh yeah, you check a thing and then you do a thing. And so, whenever you can strip the logic down to present it to them as if statements, that is easier than a lot of other like using functions that have sort of hidden implicit ifs that they don't know about, and things like that. And the last thing that makes sense, and this is controversial, is variables, eventually. Variables are really hard to explain. I'm sure any of you who have tried teaching programming will agree with me. Variables are one of the biggest stumbling blocks. But they do get there. And in fact, most of them get there pretty quickly. And so then you can keep using variables and you can build upon that, and they will understand, okay, you put something in a variable and then you can use that. And this helps keep things going rather than having a sort of implicit state or a static class or things like that. Put it in a variable and they tend to understand that a bit better. So what gets in the way? Well, this is the stuff that we want to limit. And in a way, it's kind of the exact opposite of that previous list, but we're going to start with bad names. Bad names are bad. They are confusing. If the name is not clear, it provides a barrier every time, both to just using it correctly, but also to remembering it. And the ability to actually just sit there and be like, oh yeah, I know what I have to do, that's really critical to feeling like they're achieving something, feeling like they're learning something for a lot of students. If they don't feel like they can remember the stuff that they've been learning, then they don't feel like they're learning, and they don't feel like they're achieving. Eliminate extra steps. Like we saw with the NeoPixel, where we had that extra write after we told it what pixel it is. Now, to be clear, I understand the difference between setting the color and using write. If you've not used NeoPixels before, they essentially just get treated as an array, you put your colors in, and then when you say write, the whole set of NeoPixels updates. But computers are fast. Even like little computers like a Kookaberry or a Microbit. And as far as 99% of the stuff that the kids will be doing matters, you can just write that every time. It doesn't really matter. So don't get the student to write it. I'll write it in the wrapper. Unnecessary arguments, things that are confusing, things where you have to specify stuff that should already be known, a la how many NeoPixels are there. If you can remove those by adding default arguments or even just not having them, just fixing them, that makes it a lot more approachable. Every time they have to have another comma and another thing inside the brackets, it's another question of, wait, well, where does the bracket go? And what order do these have to go in? And have I done all of them or have I forgotten one? So remove unnecessary arguments. And then remove protocols. I touched on this with I2C and alluded to UART, but when you have to follow a procedure that is technical and has many good technical reasons for existing, but you are just starting your technical journey, that procedure is impossible. So you won't do it, and that limits what you can do. Lots of really cool things. Use I2C and use UART and use all sorts of ways to communicate over these protocols that students won't manage to get to. And if you can do that behind the scenes for them and expose them an abstracted interface that offers to them what they want to do, that will lead to them having a vastly expanded set of actions that they can do, and set of features that they can implement. And the last thing I consider is that consistency is key. Like, really, this is really key. You want to build on what they know. If they have learned how to use the basic functions like print or int, build on that. Keep using basic functions that are similar to, but distinct from, print and int. If they have understood a while loop, build on that. Let them keep using while loops. Reinforce that knowledge and help them to understand how you can remix that knowledge, essentially, into all sorts of different things. So you're reinforcing these lessons. They can keep using the same systems in different ways. They will become more familiar, they'll become more confident, and they will start to achieve a lot more. And then maintain your patterns. And this more comes to when using or making this kind of wrapper. But if you start to establish one pattern, keep that going as much as possible. When you have all these different peripherals, like I showed, they're all from different manufacturers, and they all have different feature sets, different interfaces, different ways of operating, that each one is a new thing that has to be learned. And we've all come across that when you install a new library using pip, or you get a new piece of hardware and you start using its interface, and it's different to other ones, and you have to spend quite a lot of time learning that. That's time and expertise that the children don't have yet. They don't have the time with a suitable teacher because you've got a whole classroom, or you've got a bunch of kids you're tutoring, or you're running a whole event. And so you can't give them the one-on-one time that many will need to get across that interface. And then also, they don't have the expertise. They're not confident in tech. They're not comfortable with reading documentation. So you can't just say, here are the docs, off you go, learn it. They just never open that, and then they will not do tech. And then they will drop out of the class, and then they won't ever do tech again, because you have taught them it's not for them. So maintain your patterns. One that I really like to use is from English. I mean, lots of other languages, but it's what we do here. Subject, verb, object. I want my thing, subject, to do a thing, verb, about this thing, object. And we saw this with the bar light. Bar dot set pixel to that color. Same for the RFID reader. RFID reader dot read tag name. That one doesn't have an object. Not every sentence has an object. Sometimes subject verb is enough. She ran. So, how have these wrappers gone when we've used them? What kind of results did we see? So as I said before, we had 4 major events with these wrappers, and we run surveys before and after the events where the students answer a bunch of questions about what kind of stuff that they've done before, the tech that they've done before, how much have they engaged with STEM, what do they like, yada, yada, yada. And we ask them in various forms, how much do you like coding? Totaling up the surveys from these events, before the events, about 26% of students have a positive opinion of coding, and 39% don't. Clearly, that's not a lot of the kids. So how did we go with using these wrappers? Well, in the surveys after the events, 55% of the kids said that they liked coding, and only 15% said that they didn't. I think this is a huge success. This is taking kids who genuinely didn't like coding, thought, like, and when I put this together, I checked, like, are these results coming from kids who have done some coding? And I filtered down to that. And yeah, they've done coding, and they're like, yep, it sucks. I don't want to do it. But their school said they had to. So we had them. And then they did. And then they liked it. I think that a lot of the problem is, with being thrown in the deep end and being told, like, you're going to do this thing and you're going to work it out. And there's a lot here that is difficult, and then they're not given the support, and they're not coached through, and there are a lot of impediments to achieving things. And then I read through a whole bunch, like 400 kids worth of the feedback, and there was lots of it, and lots of it was positive. And one of the really recurring themes was that we made it approachable. We made them feel like they could do interesting things that they didn't think that they could do. We made them feel like they could read an RFID tag, and when the right tag was placed on the thing, you could open up a box that was previously locked, had a solenoid in it to be an electromagnet, like controlled by circuitry, controlled by the Kookaberry, locked in there, interesting things, it's an escape room. Opens up because of code that they wrote. And they can see, oh, wow, yep, when I do this, that happens. And I think that's a really important thing. I think this is, as a slight tangent, why devices like Kookaberries are really good, is because if you first teach Python using idle, as an example, and you teach them print hello world, then they type into the computer and then text appears on the computer. And also text appears on the computer when they hit the run button. It's just over there now. And like, I don't know, text appears on the computer when I type all the time. Like, that's just what happens when you type. I haven't done anything. That's just what computers do. But they understand the concept of two different computers. And they understand that the Kookaberry is a different computer with this little screen. And so when you type display.print hello world, and then you hit go, and it appears on the Kookaberry, well, now you've made a computer tell another computer to do a thing. And that's big. Like, I think that is a huge distinction that is vastly overlooked. That gets them excited. And then when you can go a step further and you have your computer tell the little computer to tell the box to unlock, you can control a lock with a computer being controlled by a computer that you typed into. That's good stuff. They like that. So, how can you do this too? Well, there's a bunch of stuff you can do. Firstly, you can check out some of the demo wrappers that I've put together on GitHub. That's our organization and the repo. I'm not about to change this slide anytime soon, so take photos if you want. That has a few of these wrappers available for you. There's a couple that are pre-compiled because also this is our business. But there are a few of them that are just there as Python files. You can have a look. You can see how I do them. You can also see the cunning way that I have that connected code library set up where you can import just from connected code, import star, and you get all of the libraries and all of the wrappers and everything. You can make your own wrappers. This is particularly good if you are not using Kookaberries, which I'll talk more about in a second. Most of you probably aren't using Kookaberries. But if you're using things like Arduinos or Raspberry Pis, writing your own wrappers might well be the way to go. Email me for advice. My email's been on pretty much every slide. It's also, there's a second email for connected code that's on this slide as well. So you've got two of my emails now. Email me and ask for advice or just show off. That's cool. I like to see what people have done. You can email us at Connected Code. And we can come to you. We go to schools and run events. And they can be little events for 4 or 5 students who just need someone to come in and do a fun project to help with a grade 11 or 12 software class. Or we can come and run a huge event. We've run ones for the escape room was 165 students, I think. The data detective was 180 students. We did it for 2 whole grades each. And they were huge events, and we can absolutely do that. And lastly, check out the Kookaberries. So the Kookaberries, real quick plug for them. The OSTEM Foundation is really cool. They do really cool stuff with the Kookaberries and with supporting educational initiatives. The Kookaberries are now available to purchase. Again, you email them and sort it all out. The reason for that process is because there had been supply chain issues, crypto miners, chip shortage, you all know that. Or if you don't, it doesn't really matter. But they're available again, so check those out at OSTEM. That's pretty much it for me. There's a nice picture, courtesy of Apple. Does anyone have any questions? Yeah. Oh, yeah, there's a mic coming. That's better, because then everyone on the recording can hear that.
For the roving mic. Wait for the roving.
Is there a mic?
Wait for the
I don't know. Do I have to just come and...
That's good tech stuff. There we go.
Ooh, yeah.
On and on again. First off, Jack, thank you so much. Can we give a big round of applause?
Thank you. Thank you. Woo. Mug.
Okay, question. I'll get on that.
Thanks very much for the presentation, Jack.
Thank you.
I had a curious question. When you're introducing coding to kids of, I don't know, no matter the age, do you jump directly for them to use hardware, like call it like a Kookaberry or a robot or a Raspberry, whatever, or do you spend some time purely with coding with things like Scratch or something that takes only like software related? So basically, yeah, the question is like to introduce them, you jump directly to software and hardware, or you spend some time with software only, and then once they know the basics, you jump into hardware as well?
I think jumping to hardware is the way to go. I think because of that distinction that I was saying about making your computer make another computer do something, I think that's a really exciting moment for a lot of kids. And I think the sooner you can get to that, the sooner you will get them interested. And this is important because the longer you take to get them interested, the more disinterested they will become, and the more kids will decide that it's not for them and they're not interested. Yes, that's a great point. Thank you, Renee, who is the CEO of Connected Code. One thing that we do for younger kids is the OSTEM Foundation also uses Blockly. They have their own slight variant called Blockly. And so these Kookaberries can be programmed using Blockly. That's great for the younger kids. The wrapper concept doesn't really apply to Blockly because there are fixed blocks and such. But we have also worked with the OSTEM Foundation to add in a few blocks when needed to essentially do the same thing. And here's a block that does this little feature, fakes a channel on a broadcast radio or something like that. So yes, great question and great suggestion. Thank you.
Yeah. Thank you, Jack. So I'm curious about what happens, and I know you said it's sort of the 1% case. What happens when the student hits the edge of the wrapper? And I know there's lots of things you could do, but I'm really curious how that pans out in the classroom and what your experience has been with that.
Yeah, terrific question. One thing that I didn't highlight as much in this talk as I could have or should have, I don't know, there's a time limit, is that with these wrappers, we aim for differentiation. So we have a few different functions. A great example is with the potentiometer, which is, I think I remember one of the demo ones, where we give them, read in a number of steps, and it will just give them a number between 1 and 20. Or you can read percentage, which same thing, 1 and 100. But we also just give them read, which lets them get the whole number as a 16-bit integer, lets them see 0 to 65535, and then they have to do the maths to work out what divisions they need. And if they get beyond that, then they can start importing in other things that the actual libraries that our libraries depend on. And that's just for the potentiometer. For other ones, you can have, we have a bunch that have optional parameters. So with the NeoPixel bar and our other NeoPixel sort of modules, there is actually an optional parameter where you can say how many NeoPixels you have. And so if you do buy a different thing, you can add in different stuff there. With the RFID reader, those you can specify an address to daisy chain them. And we just always secretly hide away the default address, but if you specify an address, you can connect more of them. And so by putting stuff behind default arguments or having multiple functions that kind of do the same thing, but with more or less assistance, that's how we let the kids who are really progressing get into the more interesting and more advanced stuff without sort of giving them a hard stop of, well, now you have to really dive in the deep end on your own, while we focus on teaching this stuff to the other kids.
Good. I was waiting to cut you off.
No.
We are out of time. I know there were more questions. I'm going to throw Jack under the bus by
Yeah, I'll
saying that
stand out
he'll be
there.
around outside at morning tea. There's also the Discord as well.
I have connected to the Discord, so
Excellent,
message me.
excellent. We have 12 minutes for morning tea. Generous time. But as you're packing up, I want to throw just a slight... The next talk is perhaps the most controversial of the entire conference. Come back to find out why. It's also about Pygame. It's really awesome. Come and join us. Thank you so much. Thank you, Jack.